Hi everyone. Last time we developed this 10-inch drone. And this 10-inch drone has several important components, and probably the core component of this drone is a flight controller. We use Matek. This flight controller has a microcontroller that is a microcontroller from ST Microelectronics, and it's the brain of the drone. Brain means that it's making decisions about how to stabilize drone if we are operating this drone in a horizontal mode, for example. It's making the decision how to control motors in a way then we'll have a smooth flight. It uses some sensors, accelerometer, gyroscope. You can connect additional sensors like GPS. If you have GPS denied environment, you can connect optical flow sensor in order to make sure that your drone is stable and even can navigate from point A to point B in an automated way. It has obviously Express LRS receiver in order to get commands from the operator. It has VTX in order to send video stream to the operator. And a few more sensors can be added to this brain. But if you would like to extend drone capabilities, especially if you would like to add some algorithms that will help to automate this drone and run some missions in a way that you don't have connectivity to the operator, for example, it's really hard to do using this microcontroller because, in fact, this microcontroller it has capabilities to execute just one main loop that uses just one single core. And this loop, in fact, just manages the drone and use proportional integral differential control in order to manage this drone in the best way. And it does not have too many computational capabilities to run any kind of machine learning algorithm, for example, or any kind of even OpenCV algorithm, just basic computer vision stuff, etc. So in order to add some additional capabilities to this drone, we need to extend the existing brain somehow. Extend means that we are not going to touch and modify the drone, but we're going to add a thing called companion computer. Let's discuss a little bit then and where we are going to attach this companion computer. And after that, let's discuss a particular companion computer that we can potentially use as a good starting point in order to increase capabilities of our drone. So I will start my explanation with just a blank sheet of paper, and let's discuss on the high level what kind of components our drone has. We already discussed that it has camera. It has camera. Camera is important in order to see their drone is flying and in order to send this information to the operator. And in fact, the operator is making decisions. In case of the automated flight, of course, we obviously would like to use this camera in order to send this information from the camera to the brain of the drone, and brain should be able to make decisions. But as for now, we are doing this, we just send signals to the flight controller. In fact, flight controller is doing nothing with camera signals, and it's even not receiving anything. But flight controller has some information about drone position, drone altitude, can just provide information from accelerometer, gyroscope. If it has GPS, it can provide information about GPS coordinates, etc. And this information is very useful probably for the operator. So how flight controller can provide this information to the operator? Usually flight controller has an OSD chip. OSD chip, it's a chip that allows to get video stream from the camera, text information from the flight controller, and combine it into a new image. And this information from the OSD chip can go to VTX. VTX means video transmitter that sent with antenna, obviously, and it sent information to the operator. And operator should be able to send commands to the drone. So obviously we have one more module. In our case, it's Express LRS. And this module is a receiver. And it just receive information from the operator and send it to the flight controller using UART protocol. So we are using TX RX pins there on the flight controller. And frankly speaking, that's all. Yeah, so most important components you can see on this schema. And now we would like to extend capabilities. And we have a computer called companion computer. So companion computer, it can be almost anything. Yeah, it can be any kind of computer. It can be one more microcontroller that can run just one single loop and has probably just single core, and you can program it using assembly programming language or like C programming language, but on a really low level. It can be a more advanced controller or CPU or anything like this that can execute Linux and potentially even have several cores and can probably execute more advanced algorithms, including computer vision. It can be even something more advanced with GPU inside in order to speed up inferencing for deep learning models. It can be FPGA if you would like to process much data and if you know what you're going to process, and you can implement some algorithms based on FPGA. It can be a combination of everything. But as for now, we just assume that it's a computer, companion computer, just like thing that provide additional capabilities. And the idea to make sure that we connect companion computer probably to the flight controller, but it's not always true. In order to manage and provide additional commands to the flight controller. And in this case, if we connect companion computer to the flight controller, companion computer can emulate potentially an operator for our drone. But in this case, operator is going to be on drone directly, and it means that we don't have any issues with connectivity. Because we are not using radio protocol, we're probably going to connect this companion computer to the flight controller directly using probably UART port. And it means that you can process some data even like with better quality, because even data from camera, they can be broken, damaged by the way to the operator, and operator probably does not have so good quality as camera potentially sent to the OSD chip and to the VTX later. So companion computer can get raw data from the camera directly. And depends on our task, we can connect companion computer to our drone in one of the following ways. Let's start with less common ways. The number one, we are not going to touch camera flight controller connectivity at all, but in our drone, you could see that we are using VTX in order to send analog signals. Analog signals helps us to transmit information to operator that is too far from the drone. More other than we're using analog transmitters, we're using some standard protocols, we're using some standard formats, some standard frequencies, etc. And everything is totally open. So you can buy almost any analog VTX on the market. Just check frequency for that VTX. Usually it's 5.8 gigahertz, and use it with any random monitor, any random analog Googles or whatever. But if you're talking about digital transmitters, usually they based on close technologies. But analog transmitters has a very disadvantage point. It just transmit data that can be intercepted by anyone who has an analog monitor on the same frequency. And it's a problem. It means that potentially like random people can see signal from your drone and see there it's flying, what it's doing, there it's landing, etc. And it can be a problem for some missions. So companion computer, for example, in this case, can be attached. Sorry, not here, but prior we send signals to VTX in order to get analog signal from here, apply some encryption algorithms, so code the signal, and after that VTX can transmit. VTX does not care, is it a clear image or anything like this, it just transmits everything that it will get from the companion computer. And of course, on the operator side, you need to have another computer that will encode your signal, and after that, display a clear image. It's like one very unusual way that companion computer can be used. Another way, the same situation, operator sends signal to ExpressLRS module, and ExpressLRS usually send these signals directly to the flight controller. But we can connect our companion computer to a point that is between flight controller and between ExpressLRS. Why? In order to intercept all ExpressLRS signals, and if nothing happening, we can redirect these signals to the flight controller. If companion computer decide for any kind of reason to start automated mission, it can just emulate ExpressLRS signals to the flight controller in own way and navigate drone depends on the situation. It's not a standard way to connect companion computer to the drone as well, but it works for some scenarios. Which scenarios? In our case, we are going to work with systems like autopilots like PX4 and ArduPilot. Both systems support companion computer, and both systems supports protocol in order to establish connectivity between companion computer and flight controller. But some systems, like Betafly, for example, they don't have capabilities to connect companion computer. But in this case, if just flight controller does not have any clue about that companion computer intercept, for example, ExpressLRS signals and transcend own signals to flight controller, in this case, it can be connected to any flight controller and intercept signals that operator said to any flight controller, even on Betafly. But it's not a standard way because in this case you are getting less telemetry from the flight controller on your companion computer. In this case, it's really hard to understand how to manage your flight, but I saw some solutions that are doing like this. In our case, we are not going to do this or this. We are going to use standard way that usually recommended in order to connect companion computer to a drone. We are going to connect our companion computer directly to the flight controller using usually UART protocol in parallel with ExpressLRS receiver. But since we are going to use PX4 and ArduPilot, usually these systems allows operator to activate some automated missions using a remote controller. Or some missions can be activated in the case of any problems with the signal. Once it's interrupted, companion computer can start sending signals to the flight controller. And thanks to technologies, and one of the technology, for example, that implemented for both autopilots called Mavlink, we can interact with the flight controller and we can manage flight controller in the same way in which operator can manage it using radio transmitter. And what we are going to do in this case, what is going to be done if companion computer is connected directly to the flight controller. once again, depends on the situation, but in most cases, we would like to work with images as well. We not just would like to send some commands based, I don't know, any kind of telemetry from the flight controller, but we would like to get images from the camera, and we would like to pre-process these images on our companion computer, apply some algorithms, and make a decision how to fly. So what is going to be in this case? In this case, companion computer connected to the flight controller, but camera is going to be connected to companion computer instead rather than to the flight controller. And in this case, camera can send signals to the companion computer. Computer can pre-process images, make some decisions what to do, and send signals to the flight controller. So in our case, we have the following architecture. We have camera send signals to the companion computer connected to the flight controller using UART, flight controller getting signals from Express LRS module or from any other module, frankly speaking. It can be Mavlink module, it can be any LoRa module that you can just buy from any kind of provider, and it's not a problem at all. And flight controller uses OSD chip in order to send video stream to VTX, and finally send to the operator. If you follow me carefully, you can ask the OSD get information from the camera, since we send stream to the companion computer, and companion computer send commands to the flight controller rather than video to OSD. What does it mean? It means that if we would like to send video to operator as well, we have two options. Option number one, we can potentially have two cameras, and one camera can be digital, for example, and send video stream to the companion computer. Or another camera can be on our hand, can be connected to OSD chip and to VTX directly after that. Or another way, we can connect digital or analog camera to the companion computer, and companion computer can pre-process our video stream. If it's analog camera, analog stream should be converted into digital first of all. If it's digital, no problem at all. We pre-process video stream, and after that, we need convert output to analog and send to ISD chip as usual, connecting, in fact, analog converter to the flight controller in a way than we connected camera to the flight controller before. And in this case, it's going to work like this. So it means that if we are taking existing drone, then we had analog camera, and once again, it can be digital as well, but we used analog camera because if you're talking about drones, usually digital cameras were associated with appropriate digital transmitters, and they are totally closed technologies. Really hard to use them if you're not relied to a particular provider of the system. But we used analog camera, and it means that analog system should be converted to digital. Companion computer can pre-process this digital signal. Depends on that, it can send commands to the flight controller. And finally, companion computer can convert video into analog, send to SD, and finally to VTX. So for our drone that we developed, our schema going to be like this. In case of non-FPV drones, then operator in fact not getting video. Of course, VTX, analog converter, and OSD is not required at all. If you're building big drone based on PixHawk, PixHawk, for example, does not have OSD at all. You need to connect an external module to PixHawk in order to have OSD chip and in order to convert any kind of video from a camera to VTX and apply some OSD information to this video stream. So I hope everything is clear here. And now we need to think about what kind of companion computer there to start. And I can see that lots of people are willing to start with something expensive like NVIDIA GPU developer modules or anything like this. But once again, we have a 10-inch drone that is not very expensive, yeah, $500 or so. And we don't have so much place inside. And we can damage it. And it's not stable enough even because it's small. It's like more a racing drone rather than something big that's going to carry expensive devices, including expensive cameras or expensive NVIDIA developer modules. So my recommendation, if you just started and if you're not sure what you're going to do with your companion computer, but you would like to make some experiments, start with something cheap. And the cheapest module that can satisfy many missions, my recommendation, use Raspberry Pi Zero 2V. Why? Because first of all, it's small. And if you're talking about this module, it can be placed with no issues inside a 10-inch drone, or it can be placed even inside a 7-inch drone. So you can see I have my drone and I have enough space between camera and between flight controller. And in fact, I can print even a box here and it accommodate my board, and I just have some wires that are moving outside of the box in order to connect camera and in order to connect companion computer to the board, and that's all. Oh, you can print a board and place it somewhere on the top and you have enough space for a battery here as well. So my recommendation, use something like this that is small, and the most important, it's cheap. You can see that this stuff costs about $15, and it's exactly the price that I paid buying this stuff on GGK, or I don't remember exactly which provider, but it costs exactly $15. Of course, as I mentioned earlier, we need to make sure that we have a couple more additional components, and you probably could notice that we need converter from analog to digital, since I propose to use the same camera that we installed last time into our drone, and we need digital to analog. And that's why we need an additional component. So we have a Raspberry Pi, and we need to buy probably a cheap analog to digital converter. I'm using this one. This one can be broken into pieces, and in fact, you can use just central piece for your final design. And it can be like very small inside the same box that probably you can print for your Raspberry Pi 202VW. And another benefit of Raspberry Pi, it has analog output. So this component converter from digital to analog is not needed for Raspberry Pi 02W because it's already here. And if you look at pins on the back side, you will be able to see pin code TV. And in some documents, you can see that you just need to connect your VTX or SD chip in our case, so connect this pin to the flight controller. There you connect usually your camera. It's not true. I don't know why this labeling is so inaccurate, but in fact, pin that you need to use is here. It's marked AB. It's on the left from TV sign. This pin that marked as TV, it's a ground, in fact. You can use it as a ground if you want, but then we are talking about analog output. It's here, and latest Linux operating systems that you can install on Raspberry. Raspberry, for example, it automatically will transmit output to this pin if HDMI is not connected. And obviously, if you add this board to your drone, HDMI is not going to be connected, so you have analog output from here, from this pin marked like AB. And it means that we don't need any additional device in order to convert our video from digital to analog. The only thing that I would recommend to buy is a DC converter that allows us to get voltage from the battery and get stable 5-volt output. Why it's happening? Why we need it? First of all, because this Raspberry requires 5-volt, and you can say, okay, 5-volt I can get from my flight controller. And yes, it's true, but you need to be very careful. So if you look at documentation for this board, and if you go to getting started, you will be able to see, even on the first page, how many amperes required to produce enough power for this board. And you can see 2.5 amperes. And for Raspberry Pi 5, you need even more, much more. But 2.5, and if you look at different flight controllers, you will be able to see that, yes, pins can have 5 volts, but they, in many cases, does not produce enough number of amperes. So let's look at several boards. One of the boards that is really a standard for 7-inch drones, at least was a standard. It was a board from a company called SpeedyBee. And this board has several versions, and first version, for example, that I started to use, it was F405 version 3. It's pretty old, but still possible to buy on Amazon. And the problem that if you look at this board, you will be able to see that there 5-volt output, and this 5-volt output provides up to 2 amperes. Moreover, when we are talking about 2 amperes, we are talking about all devices that connected to all 5-volt pins. And if you have 2.5, and if you have something else rather than your companion computer, you don't have enough power. Moreover, SpeedyBee and many boards have pins called 4.5 volts. These pins can be powered from USB, and it allows you to set up, for example, Express LRS module. They will now connect your drone to a battery, and you can see there 1 ampere watt. Version 4 is a little bit better. Version 4 provides 3 amperes, and it should be enough. But remember that you're going to connect something else rather than companion computer. So yes, potentially you can use 5-volt pin, and you still cannot use 4.5-volt pin. In case of Matek, situation is a little bit different because we have stable 2 ampere for all 5-volt pins, so not enough. And officially you cannot connect your Raspberry Pi to any 5-volt pins. I'm not sure about 4.5 if I have, but once again, you can see that VBAT filtered output is 1 ampere for VTX and camera, and it's the same, not a good pin to connect even DC to DC converter. That's why my recommendation, look at specification for all the boards and connect your companion computer to the battery. Your flight controller and your companion computer are going to share the same ground anyway, because it's the same battery. But if you use a good adapter, I have this one that is like an adapter allows me to regulate voltage. I don't like adapters with regulator. I have another one, it's much smaller, but it provides a steady 5-volt output. Usually you can find converters in this case, it's something up to 36 volts, I believe. That is good enough for 6S battery. Check parameters very careful. You need to make sure that your input not less than battery can provide to a drone, and you need to make sure that you're able to get stable 5-volt and at least 2.5 ampere. This adapter provides 3 amperes, so it should be good enough for my board. And obviously connect it to the battery, and after that connect it to Raspberry Pi. So let's look at pins on Raspberry Pi 0, V2, 2W. And let's look at my implementation of this design. So I just used a search system in order to display pinout for Raspberry Pi. And what we need to use here. Obviously, we need to provide power to our board. You can see that these two pins, and they are here, pin 1 and this, I'm not sure about numbers, but these two pins, first two pins on the right, if you're talking about our board, from that side we have SD card. They have 5-volt, and they can be used in order to provide power here. And another pin, pin number 3 next to them, is going to be ground. So use these 3 pins, 2 of them in fact ground and 1 5-volt, in order to provide power to the board. Be very careful here, because obviously what you're going to do, you are going to connect your DC-DC converter to the battery, and after that you're going to connect your companion computer to this DC-DC connector. Usually, in order to do any kind of development, I have at least 2 boards like this. In some cases, I have 2 boards. In some cases, I'm using a bigger analog. For example, I'm using Raspberry Pi 3B here in order to test software for this Raspberry Pi 02W prior to upload software to this chip. Why? Because this board, it's easy to set up. You can connect keyboard, you can connect mouse, Wi-Fi is enabled, so usually I not use mouse and keyboard directly, but I set up Linux here, connect to this board using SSH, and this board can be connected to a monitor using HDMI, and I can see what I'm getting from there. And you can use the same adapter in order to connect it to the board to USB, and after that use another camera to validate your solution. In fact, you even can connect digital camera if you would like, But this is my test stand for my solution. I'm not using, obviously, this board for development because it does not have enough connectors and it's like pretty small. It has almost the same power, yeah, but due to number of connectors, I prefer to use a bigger version of it. It has the same chip. It's a little bit faster. Of course, I don't recommend to use this one for your drone and use Raspberry Pi 5, for example, for development because they have totally different chips, totally different speed, and it means that if algorithm works here, it probably will not work here. This is my usually test stand, and I'm using it to do development. But once you connect this board to the drone, the only way to update software, remove your SD card from the board, copy everything what is needed, or another way, use SSH, but drone should be connected to a battery. And it's not very convenient. Why? Because battery potentially can be discharged fast enough, and it will require to recharge it every time. The second, it will power other devices on your drone. Some of them can be very hot in few minutes because your drone is not flying and there is no any kind of wind and anything like this. Your drone is like located on the table. And there is a question why you cannot connect it just using QSB. And there is a problem. If you connect it using QSB and these pins are connected to your power adapter, depends on the DC to DC converter, it potentially may damage your converter itself because in many cases, cheap converters don't have any diodes inside. So what does it mean? It means that once you connect your board using QSB, you have 5 volts here that will start powering your DC-DC adapter from opposite connections. There is an arrow and you have 5 volts here as an input and it will damage probably your DC thing and you will be lucky if it doesn't damage anything else. But in many cases you will see smoke. You will see smoke, I saw it many times because even I'm forgetting that I cannot power this board once I connect it to the drone. That's why, yes, it's important to have a test stand that is not connected to a drone in order to test our initial software. And after that, power your drone, upload all needed software to this board, and after that, you can fly and test your software on a real drone. So it's like one important warning to you. Next one. I already told that video can be connected, video output can be connected to this pin. So you can send output from the board to a flight controller using QSAB pin. You need to connect input. Obviously, depends on the adapter, but in our case, we use an adapter that supports USB. Linux, and it uses driver that recognized by Linux automatically, so it's called driver 3 or driver OS adapter or anything like this. And you need to connect this using QSB. Obviously, this connector will not fit, and I would not recommend to buy any adapters because you have too many things connected to your board and it will be really hard to place it inside the drone. You can connect, remove this USB connector from the adapter, just break it and connect this adapter using wires directly to your USB pin. And here you can use small adapter or you can use solder your wires directly to USB pins that are here, or you can even desolder with USB if you have these capabilities to do. I'm using usually very small adapter that connected to wires and connected to my analog to digital converter. So it's not a problem. You're not using any kind of pins here, just USB. And finally, you need to connect this companion computer to your flight controller. It can be done using UART. In Raspberry Pi, you have two pins that can be responsible for UART. You can see GPIO 14, GPIO 15, UART TX, UART RX. So pick any random UART that is free on your flight controller and connect TX to RX, RX to TX. That's all. And after that, your board is connected. I already assembled a drone, and let me show how it works. Connected power to battery pins rather than to battery directly, but these wires can be connected to battery, the output directly. And after that, you can see I'm using DC. DC, this one is not regulated, it provides steady 5 volt here. And a regulator provides power to my Raspberry, and you can see that I'm using this first pin for red wire and this third pin for black one for ground. And as I mentioned before, I'm using TX and RX here, two pins next to the ground, and white in my case it's TX, green it's RX. So it means that I'm connecting TX to RX, RX to TX here. I just picked this UART port. Cannot see which number here, but it was empty in my case. I'm just connected this port to this UART port. And in our case, we have how many? 1, 2, 3, 4 cables. And obviously I have one more cable. I explained that before. Cable that connected to TV output. It allows me to get my analog signal and send it to the standard pin on flight controller. This pin connected to SD, SD sent it to VTX. And finally, I have this adapter that I demonstrated to you, but I already broke it in pieces. And this adapter connected to USB. And in this case, I have to connect all 4 cables, ground, power, and 2 more USB related cables. You can see them in specification. And from another side, all what I need to do, just connect my camera. Camera connected using ground and power cables to the flight controller. As usual, I did not disassemble it, but I just desolder a cable that was connected to camera pin and connected to camera pin on this converter. And I already installed Linux on this board. This is not like Raspberry, but it's a Linux based on build root. And what we are going to do, we are going to check if everything is fine. This board should at least send video signal to the flight controller. Flight controller should be able to attach OSD information to video stream, send to VTX, and VTX should send this signal to everybody who are interested, and I should be able to see output using a video monitor. Let's take video monitor and let's try to power this drone. I would like to say that I installed to this PDB board R2Pilot because I'm going to use Mavlink in order to establish communications, and R2Pilot is very important in this case. So it was originally Betafly, but I just installed R2Pilot. Let's take a battery and let's take a monitor. I hope you will be able to see everything. I'm connecting my drone to the battery, and something happening to my monitor, and it looks like that it was a wrong channel, but right now you can see that I have an output from my Linux on this companion computer. And it displays welcome to build root. It means that it's like my Linux that I use build root in order to create it. And you can see some information on top of this Linux screen. You can see amount of volt that I have in my battery, amount of ampere that my drone is consuming right now, and some other information. It does not look very awesome. Probably you don't see it very well, but it's here. And it means that, okay, I am getting another output from my Raspberry, and I'm overlaying this information using KSD information from my drone, and it works. And now, obviously, next step, we need to create software that will be able to execute on our board, grab video stream from the camera, preprocess it somehow, and send output to OSD chip and finally to the operator. And there is a question, if it's possible to preprocess any kind of stream using this small companion computer. The answer is yes. If you're not using obviously machine learning or deep learning, you can get at least 640 by 400 images, and frankly speaking, our camera is not going to provide much more, and preprocess images with frequency at least 30 frames per second. This chip has these capabilities, and it's more than enough for many missions that potentially would like to execute. But today I'm going to stop and play with your own companion computer. If you would like to connect something else, check if it has another output, try to find a way how to configure it. And next time we will discuss programming for Linux, because here we are going to have Linux. Thank you.